Kereš, who will talk about, which is no longer a tentative title, galaxy formation with cosmic rays.
All right. Thanks for the organizer for inviting me. It's really great to be here in this 3D Zoom session. Feels almost live. And yeah, sorry, I had to modify my talk title a little bit. So this is the work done with many different collaborators within FIRE collaboration, and I'll show lots of results done with TK Chan and Phil Hopkins and Sochin G. All right, so just brief outline. I will try to go fast through the first half and then slow down in the second half. So I'll just try to motivate inflow and outflows in simulations and what we know for many, many years. Then I'll talk a little bit about stellar feedback in FIRE and adding cosmic rays into the mix of stellar feedback. Discuss successes of the simple cosmic ray model and then potential complications and issues, just to say that we don't really know the true answer yet. All right, so this is the picture that you know from from many, many years ago. We think that the way we supply galaxies with gas for star formation is through these intergalactic filaments at high redshift, and because the structure grows fast, filaments are supplying lots of material into the galaxy so they can form stars very fast in early times. At late times, most of the halos, especially Milky Way and higher, are filled up with the hot gas that can slowly cool onto galaxies that probably supply galaxies with gas at current epoch, and it's probably responsible for formation of the thin disk that we see around us. All right, so this is all great, but as we know, the infall itself, it's not good enough. It can form galaxies, it can supply them with fuel for star formation, but it produces galaxies that are way too massive. So this is just an example of the actual observed mass function from Bell et al. Here. And this is the example of mass function from simulations that do not have stellar feedback, and this would be roughly the scale-up version of the halo mass function. So you see that galaxies tend to be way too massive here at the low masses and also at the high mass end. So we need something else to prevent too much mass buildup in the galaxies, and that's something we believe it's related to young stars, especially to supernovae, and we know that since 80s, supernovae add momentum and energy into the interstellar medium, and for certain conditions of galaxies, they can actually provide large-scale alpha from the galaxies. So we think that you have this low mass end, we are regulated by the young stars and by supernovae. At the high mass end, there are still discussions what that could be. It's most likely connected to feedback from active galactic nuclei, but that's not something I will be talking about today. All right, so we see outflows everywhere. Right now, we only see it in local starbursts, but early on, we see it in every galaxy we look at. Like the spectra typically show blue shifted component that it's indicating of gas being kicked out of the galaxies. But this is a really tricky thing to model because we might have a galaxy-wide process or maybe even halo-wide process that starts at parsec scales where stars are exploding and interacting with the interstellar medium. So that's why it took community many, many years to actually develop models that are working quite well. So overlying question of my research is how does the interplay of gas inflow and outflows actually govern evolution of galaxies over time. So the way we address this question is by using FIRE simulations. You've seen many different talks, and you'll hear a couple of more about FIRE. These are simulations that have a relatively high resolution. In tiny dwarfs, we can go to like 30 solar masses, and in massive Milky Ways, we are like thousands or even tens of thousands of solar masses. Resolution is such that we typically resolve where the giant molecular clouds are, and sometimes within giant molecular clouds at dense pockets where stars are forming. And the key for producing outflow from galaxies is to have spatial and time correlation of star formation and supernova feedback. And that way you have a lot of energy, a lot of momentum at the same time in the same place, and you can provide this global outflow that you see in the movie that is running here in the background. We also add all kinds of feedback processes related to young stars, photoionized H2 regions, stellar winds, photoelectric heating, radiation pressure, and supernova energy and momentum. And kind of key component of FIRE is that treatment of momentum from supernovae is such that it yields practically resolution insensitive terminal momentum. So even if we cannot resolve Sedol-Taylor phase, which is almost most of the time, we are getting the right momentum for the push of the surrounding material from supernovae. All right, again, this is all relatively old topic. Once we add all these physics into the galaxy formation simulations, we are combining the infalling gas that it's feeding galaxies, and now we have these episodes of outflows that you see at early times and maybe lack of outflows at late times. And the result of these kind of simulations is a pretty good agreement with stellar mass functions of galaxies, or if you flip things around, in this M star M halo relations for galaxies. So this is all the result from like Fire 1, but it's illustrative of what we kind of do. These are dwarf galaxies whose stellar component has been lowered by a factor of 100 or sometimes even 1,000 with respect to what would happen if you just keep accreting gas into them. And these are Milky Way mass galaxies whose stellar mass got lowered by a factor of 2 or 3 with respect to what would happen if you just let gas being accreted into components. And we do it just by careful treatment of energy and momentum from stellar populations and assume IMF that comes with it. All right, so the reason I'm telling you about this is that just to motivate that we seem to understand what's going on in galaxy formation, but as you will see, once we add simple modification to physics, we may actually flip things around in many different aspects. So at high redshift, the key for producing these low masses is this strong feedback or strong outflow from galaxies. So this is a tiny little galaxy going from redshift around 5 to 2, 4.5 to 2, and it varies between a few times 10 to 7 to about 10 to 8 solar masses. It's in a really small halo, and it's producing star formation in this bursty fashion. That's the black line, and it produces then strong outflows. That's the red line from the galaxies and even from the halo, which is a little lower. So early galaxies are really chaotic and bursty, and they're like popping their stars and then kicking material out pretty rapidly. And this is the key how you lower their mass. However, by the time we get to low redshift, things change. And galaxies at late times, especially after a redshift of 1 or half, basically have Milky Way mass galaxies have almost no outflows in our simulations. They're producing stars, this particular one at relatively high star formation, and outflow rates drop dramatically to be almost close to 0 or 0.1 or 0.2 at redshift 0. So this is what happens if you have classical input of what the young stars are doing without any extra physics that it's going to come later. So should we just say everything works great? We are forming these nice disky galaxies that you've seen on my first slide. We are kind of producing crazy galaxies early on and less crazy at late times. But the question is, did we include all of the physics that should be included in these kind of simulations? So our agreement with observations is pretty good. This particular galaxy here might be a little bit more star forming than we would like, but overall its mass is not that crazy. And we try to add metal diffusion, magnetic fields, MHD, viscosity, conduction. These all affected things slightly, but nothing in a dramatic, systematic way. But one obvious ingredient that we didn't try until recently, and people did point out that it's important in interstellar medium, are cosmic rays. So cosmic rays are believed to be produced in strong shocks, mostly in supernova explosions. And about 10% of supernova mechanical energy actually goes into cosmic rays themselves. And you might think about 10% that's nothing, 90% is still in supernovae. But supernovae can actually cool locally, depending how they interact with interstellar medium. But cosmic rays can actually diffuse far from supernovae, so over time they can actually build up significant pressure in the interstellar medium and maybe beyond. So we need to account for this, even if simulations seem to be doing decently without them. So the way we accounted for cosmic ray feedback is that we developed mostly Phil Hopkins and my student TK Chen, the two-moment simplified transport scheme for transport of the cosmic rays, and we couple it with fire feedback. Similar schemes are also available from other groups. We have input relativistic fluid with 10% of supernova energy. Those are our cosmic rays. we have losses for cosmic ray, hadronic and Coulomb losses and streaming losses. And early on, we try a very simple approach where we only have one energy bin, because cosmic ray energy density is dominated by few GeV protons, and that's basically what we are evolving. You can argue about this and say, okay, we are just evolving fixed spectral slope and the whole population, but basically we have one bin. The problem here was that we didn't really know how to transport them through galaxies, because diffusion coefficients, so how quickly they're being diffused through interstellar medium, was not very well constrained. And old simulations in this field use pretty low diffusion coefficients that, if you allow cooling, would actually not do much. They would just cool out in the galaxy and not really live anywhere. So we tried different cases from 3 times 10 to the 3 times 10 to 27 centimeters square per second. Units are not important here, all the way to 100 times more. We try adding streaming, we try adding anisotropic diffusion versus isotropic diffusion and so on. But the question was, which one of these is right? So you can have a variety of outcomes. So we wanted to constrain this transport to know which one we should use to actually study galaxy population. And unfortunately, there is not much out there in terms of observations that you can use. One of the most direct ways to constrain transfer of cosmic rays is by looking at the gamma ray emission of nearby galaxies. So Fermi observed several nearby galaxies, here plotted as these empty symbols, and it found how much gamma ray emission they are providing, and we wanted to see, are we matching those observations? One thing that can happen if you are converting all of your cosmic ray energy into the maximum possible gamma rays, you have this line here that it's called calorimetric limit, so you cannot produce more gamma rays from cosmic rays than that. And if they're not losing all of the energy into production of gamma rays through pions, then it most likely means that they will escape from the galaxies. So for low diffusion coefficients, there are a bunch of points here. We find that we are just cooling too much. We are producing too much gamma rays compared to observations for low mass and even Milky Way mass galaxies. The starbursts seem to be actually close to this calorimetric limit, so we cannot really say exactly what should we do with transport there. But we know that to match most of the observations, we needed to go to relatively high diffusion coefficients. And the consequence of these relatively high diffusion coefficients is that cosmic rays can now leave galaxies and maybe do some damage outside of galaxies. So it's effective diffusion that we found that works. It's something around 10 to the 29 centimeters square per second. And that's basically what we use to now run cosmological simulations with that kind of transport to see what happens to galaxies and their surrounding when cosmic rays are operating in there. So just remember, those are the same galaxies that work okay with fire feedback itself, but now we added this extra component with just 10% of their energy. So 90% of energy still went to the same supernova channel that was doing everything that you've seen in the movie before. So Phil ran a lot of simulations, cosmological simulations with this cosmic ray transport and with our favorite and not favorite diffusion coefficients. And it turns out that there is all kinds of outcomes you can get from this, but I would just, for now, focus on the points that say hydra here, these squares, and the circles that show our favorite cosmic ray diffusion coefficients, and they're plotted here and here. So you see that while they're not affecting so much low mass galaxies, they're definitely affecting Milky Way mass galaxies and halos. And the outcome of this extra physics is that we tend to get lower stellar masses once the cosmic rays are included. And the reason for that is that our star formation rates in Milky Way mass halos tend to drop by a factor of 2 or 3 at late times. So early times are not very much modified, but at late times, especially once we have hot halos, or we expect to have hot halos, they seem to be dropping by a factor of few. All right, so we were maybe slightly above them starting halo, now we are slightly below, but let's see what's the cause for this and what are they actually doing in practice. So I'll just briefly say that the reason that they're not doing much in dwarfs is that dwarfs are not producing much star formation, and star formation and supernovae are source of cosmic rays, so we're just not gonna add much extra support from cosmic rays even when they are leaving the galaxy. And the reason they are not super important and high redshift, although we haven't explored this in detail, is that circumgalactic medium is too dense, so it's hard to stop its infall. Potential wells are too deep. Again, it's hard to stop infall. And cosmic ray losses are higher because gas densities are higher. So all of these conspire cosmic rays not to be extremely important at high redshift, but to kind of peak in its importance in hot halos around Milky Way mass galaxies at late times. All right, so how do they make this change? What happens there? Well, it turns out that they actually modify pressure support in circumgalactic medium, and that's the key for their modification of outcoming galaxy formation. So on the left, it's an MHD simulation of Milky Way mass galaxy that shows roughly how much support do you need to support against gravity, here with black line. And in Milky Way mass galaxies, in normal fire-like simulations, in the inner region, this support comes from the kinetic pressure or kinetic component. That just means galaxies are rotating. That's why they're not collapsing. When you go out in the halo, there is still some contribution from rotation, but like it's factor of several at least below what's needed to support against gravity, and you're supported mostly by the thermal pressure, so by the hot gas. Once you include cosmic rays, things definitely flip around, even though it's only 10% of energy that goes into them. Again, the central parts are supported by kinetic component because galaxies are still rotating, they still look like nice disks. But instead of thermal component being dominant in the halo, now the cosmic ray component seem to be dominating in the halo. So because they escape from galaxies and they have to escape to match gamma ray emission, then they build up pressure in the circumgalactic medium. And they are doing all kinds of crazy stuff now there because you have non-thermal pressure dominating your CGM. So things that we learn about clumping, cold gas, hot gas, everything will change to some level. All right, so one thing that changes is this coexistence of phases. So this is from work by Sochin G. So in the standard picture or in the standard fire simulations at least, when you have different multi-phase gas in the halo, if you have a cold component, it will tend to be much denser than the hot component. They're roughly in pressure equilibrium. There's diffuse hot gas and more clumped up cold gas. And the other phases are in between. Now the thermal pressure is subdominant. Cosmic ray pressure determines what happens in the halo. So you can have these phases coexisting at the same density. There's actually an analytic solution for what density will be in perfect balance with cosmic ray pressure gradient, and that's roughly this density here. So it's this weird case where you can have cold clumps or clouds that are equally dense as hot surrounding medium. So you can have relatively low density cold gas in there, which is actually kind of pretty cool because from observations of circumgalactic medium, we found that there are many relatively cold absorbers in CGM whose exact temperature and density structure was really hard to explain if they are confined by the hot gas. They just seem to be too low densities from work by Jessica Berg and others. All right, so that's one thing, you modify the phase structure in there. The other thing you can do, and I selected the most extreme case just to illustrate that it's not always this crazily different, is that you can produce cosmic ray winds. So at low redshift, as I show in the movie, typical Milky Way mass galaxies with standard stellar feedback, they're not driving much winds. It's a tiny mass loading. You might have some hot gas venting. Occasionally, you might have some fountains and recycling, but you produce hot bubble, it just comes back to the galaxy. When you have cosmic ray pressure, if you produce hot bubble or super bubble, it might start being lifted up by the cosmic ray pressure. So they might not drive winds from the deep in the interstellar medium, but they might start driving winds from few kiloparsecs above the disk plane when they start dominating pressure. And the consequence of this is that because they're dominating throughout the halo, that might drive these slow winds that can go very far. As I said, this is the extreme, but it illustrates phase-on and edge-on galaxy picture. This is without cosmic rays. This is with cosmic rays. The bluish contours are showing inflow, and reddish contours are showing outflows. And note the scale. This is like a megaparsec scale. This would be our virial radius. That's where info gets confused because there's virial shock. Doesn't matter if you look phase on and edge on. With cosmic rays, situation is different. It's almost as if there was no virial shock, or it's much weaker than it was without cosmic rays. And you can have these slow moving with tens of kilometers per second winds going very far. Even like the megaparsec scales, they're starting to turn somewhere there, but you can actually do a big damage to CGM, maybe even IGM, depending exactly on the case being considered. So I just mentioned that you can, because of this non-thermal pressure, you can modify even virialization of late times halo. So this is again illustrated by work by Sochin G. So this is a simple case of simple transport as possible, fixed diffusion coefficient anywhere, everywhere. So reality will be slightly different than this for sure, but we are just illustrating how much damage this tiny fraction of energy can do around galaxies. So this would be MHD case, and this is a temperature, and this would be radial velocities here. So again, info is trying to get in the halo, it's shock heated, and then it can accrete from the center again. But the halo is hot. Halo is roughly at 1,000,000 degrees. That's the standard picture we know and love. Once you add cosmic rays, they do two things. First of all, they provide this extra pressure, so they slow down the inflow. Second of all, because they slow down the inflow, they keep more gas in the halo, so they enhance cooling. So those two effects conspire to have much weaker shocks, and you kind of sort of virialize some of the edges, but most of the halo stays at temperatures of 100,000 or a few 100,000 Kelvin. So much lower they would be in classical picture. So it's kind of cool that, as I said, small addition to something that almost worked is making these big changes. So it's something we should push harder to understand, and we should improve transport to know exactly what are the consequences at the late-time galaxies. So just to dwell on that point that the CGM, it's colder, of course that has consequences, and it actually works in the favor of matching low ions in the circumgalactic medium. So this is example for a single Milky Way mass galaxy. And these are different ions, hydrogen, magnesium, silicon, neon 5, oxygen 6, and neon 8. This bluish wide line are, I think, 800 square sidelines through the halo in our simulations. And different points are observations or limits. So for hydrogen, we were okay, maybe a little low overall, but it wasn't crazy. But once you add cosmic rays, you lower the dispersion of the potential conditions in the halo, and you seem to be matching the hydrogen observations much better. One thing that was a nemesis for galaxy formation models is this oxygen 6 that likes to come from a few 100,000 degrees gas. And in normal simulations of fire, we would be below it by a factor of few. But now, because our temperature is not mostly million, it's mostly a few 100,000, we are actually matching it quite nicely, and that works great. The regions where there are potential issues is these very high ions that seem to be coming from hotter gas, neon 8, it's not clear if you're doing well or not. And in a recent work by Tik and Chen, we showed that X-ray emission, it's okay close to the disk plane, but if it continues far from the star-forming galaxies, that might be an issue for this simplest possible picture of cosmic ray transport. All right, so before I finish, I just wanted to point out something that I think Phil will talk much more tomorrow, is that this is still all uncertain. It seemed great for certain things, but maybe not the best for some other things, is that there's still a large possible range of outcomes once you add these cosmic rays. So what we did, we had fixed diffusion coefficient everywhere. That's almost certainly not true. We know that it should at least scale with energy, and it should probably scale with local conditions in the ISM and CGM. But the microphysics of small scale in ISM is still unclear. I mean, we have the resolution of like 10 parsecs or 50 parsecs, but there's all kinds of deviations to the magnetic field structure at those small scales, all kinds of potential dumping mechanisms in there that we don't quite understand. So we should really work on understanding of cosmic ray transport to know what they do to galaxies. And this is illustrated in this plot from one of the Phil's papers. These are different kind of ways of transporting cosmic rays. They all roughly match this gamma ray emission. So in ISM, they're doing similar things, but once they leave galaxies, they typically go faster through the circumgalactic medium, so they don't build up as much pressure there. And the consequence of this is that the lowering of the stellar mass that was factor of 2 or 3 before, now it can be only 50% or only 30%. So we need to understand which of these is the right answer. And also, the way they modify the CGM, they can, again, lower temperature by a factor of 2 instead of factor of 5 or 10. So we need to understand what exactly is the right answer there. All right, so just a brief summary. So cosmic rays are important ingredient in galaxy evolution, especially in low redshift L-star galaxies. And to match gamma ray observations, most cosmic rays seem to need to escape from galaxies. But exactly what they do outside, still an open question. So in the CGM, escape cosmic rays can provide non-thermal support that can drive warp winds and change the process of gas accretion, and of course change observables that come with it. And details are uncertain. They can have potentially dramatic consequences for gas flows around L-star galaxies, but we better understand those details before we make even stronger claims. So this is kind of a shameless plug that has nothing to do with cosmic rays, but I have a student that will be on the market this fall, Caleb Choban, so he works a lot on dust implementation in fire simulation. So if you want to know more about this, just find me at the break. So I'll stop there. Thanks.
Thank you, Dušan. Questions?
Thanks. 2 quick questions. One, you mentioned that at high redshift, you don't find the cosmic rays are affecting very much the star formation histories or the stellar masses. I wonder if they do affect the ISM morphology in any meaningful way. And the second question is about the cold absorbers that are dominated by cosmic ray pressure and therefore very low density. So there was this nice paper by Dylan Nelson from a few years ago showing basically the same effect just due to magnetic fields. We're finding similar things in the context of the streams. I wonder if you can comment on how much of that effect you really need cosmic rays for versus can just be done with MHD.
Okay, so the first question, we did not look at ISM at high redshift in detail. So usually at low redshift, the lower diffusion coefficients do more damage in terms of pressurizing the ISM than the high diffusion coefficients. In that case, they cannot escape and they can cool a little bit more efficiently, so it's worth checking. I don't know the answer. For magnetic fields, that's an interesting question, and there is a almost like bimodal distribution of the strength of magnetic field that people get when they implement feedback that is not local. So when they have prescribed feedback that decouples from galaxies, they tend to get magnetic field strengths that are a little higher, and the same higher strength propagate in the CGM, and they can do them, therefore more damage than in our case. When we do careful check with strength of magnetic field as a function of density from ISM, there's a recent work by Sam Ponada, Phil's student. We seem to be matching that in large way. The other group claims they're also matching it. So I don't know what's the right answer, but the reason for that different explanation is the strength of magnetic field tends to be higher in the simulations that don't have localized feedback. Or at least localized feedback is not strong enough because it tends to disrupt magnetic field structure.
More questions? Apparently Daniel's question has been answered already. Yes.
Just a quick addendum to Dušan's answer. Even for the same magnetic field strength, there is a second order difference in the phase structures because many people, I think yourself included, have shown a stratified, strongly magnetized medium can have a cool diffuse phase, but it's formally unstable as well. So you'll also get denser structures forming. Whereas a stratified cosmic ray dominated similar medium is stable, so you don't form the tail of the very dense structures as much. So there will be some differences still, I think.
David?
Along the same lines, is there a chance that maybe when observers observe how galaxies are ablated in rich clusters, maybe even groups, maybe the way the ablation and the gas are distributed and the temperatures of them might give you a clue whether the cosmic rays are partaking in that medium. Because I assume that the magnetic field is transported and support will change the amount of ablated gas and the structures and how the density distribution. Is that possible observational test?
The groups and clusters are great, but they're tricky because then you might have cosmic rays that originate from active galactic nuclei in the center. So it might be in a little different regime than more disky galaxies. But any constraint of magnetic field in the CGM, which we have almost none, we have limits, would be amazing constraint to know at least the magnetic field part is out of the equation, and then we can worry on the cosmic rays purely. So yeah.
While Frank sets up, any other questions? One final question? No? If not, let's... Why not?
I had a question about the relative fraction of internally generated cosmic rays versus the, the exterior ones in the CGM, say.
So in the current implementation, we only have internally generated cosmic rays. We did not include like large-scale shocks as a generation of cosmic rays. But that can be important in clusters especially. So.
Okay, thank you. Let's thank Dušan again.